NASA calibrates its finest space telescopes to measure how much dark energy is out there. The result is mind-blowing. It dominates the mass of the universe by nearly 3 to 1. And the more space expands, the more dark energy there seems to be.
Dark energy is the energy of nothing, and it's repulsive. Therefore, as this dark energy repels galaxies, there's more of it. There's more vacuum, and so there's more repulsion. And perhaps that's the reason why the universe is accelerating right now rather than slowing down.
Dark energy seems to kill the Big Crunch theory, but scientists aren't yet sure how dark energy, expansion, and space are connected. If a volume of space doubles in size, does the dark energy inside double too? Or does it increase more? A one-to-one relationship leads to a steady expansion. The universe ends in a big freeze. But if dark energy increases above and beyond expansion, a new, even more terrifying end awaits the universe, a Big Rip.
In a Big Rip scenario, the expansion is so great that even the galaxies begin to expand internally, which means that literally our bodies are going to be ripped apart.
Scientists calculate how the Big Rip will play out. One by one, the galaxies in the night sky will blink out as space pulls them away from the Earth faster than the speed of light. 60 million years before the end, dark energy overcomes gravity on smaller and smaller scales.
First, galaxies start to rip apart. Then insides of galaxies will begin to rip apart. And then solar systems will begin to rip apart. Then planets. And then rocks, people, atoms.
The end will be mercifully quick. In the space of a few minutes, all the stars and planets in the universe will be destroyed. Their remains pulled apart into ever smaller pieces, until finally, when the universe has less than a second to live, the subatomic particles that made all matter will be destroyed, and all that remains will be the individual photons, becoming scarcer and scarcer as the space between them expands.
All you're left with is very low energy light that gets stretched and stretched until it might as well not exist at all.
The empty vacuum of space itself will be the last thing to go.
It'll be pulling on the universe so hard, it could tear the fabric of the universe apart. Reality could dissolve.
Will the universe end with a Big Rip or a Big Freeze? The answer is locked inside the mystery of dark energy. Solve that, and the fate of the universe becomes clear. The end of the universe is coming, but how will it play out? For a time, a Big Crunch was the likely answer. Dark matter, the invisible bulk of the universe, causes space to fall in on itself. Galaxies collide. Planet merges with planet. Everything becomes hotter and hotter, denser and denser.
The universe is like one giant star.
Dark energy kills the Big Crunch theory. It acts like rocket fuel for the expansion of space between galaxies.
They're not just coasting, they're getting pushed outward.
Only two possible fates remain, a Big Rip or a Big Freeze. Both scenarios rely on dark energy. For the universe to be torn to shreds in a Big Rip, dark energy must increase exponentially in the future. A Big Freeze requires a steady increase in dark energy, pushing galaxies apart.
We can't write the last chapter of our universe until we understand the nature of dark energy.
May 2009. the European Space Agency launches the Planck satellite to search for the birth of dark energy. Its ultra-sensitive telescope peers through space and time, back through billions of years, toward the beginning of everything, to capture this. This is our universe as it appeared 13.5 billion years ago, just 380,000 years after the Big Bang.
So what Planck has done is take a picture of the early universe and told us about what the early universe is like and given us our most detailed and accurate picture of that moment in time.
The universe in this picture is a hot soup of protons, electrons, and photons. Hydrogen atoms have just started to form, and it's the light from this genesis of matter that we see here. Blue areas are colder, reds are warmer.
Eventually, those hot spots, those red spots you see in the map, are going to form large superclusters made up of hundreds or thousands of galaxies. Each one of those galaxies will contain billions of stars.
Gravity and expansion alone appear to drive the formation of these embryonic galaxies. Dark energy doesn't seem to have switched on yet. So when did dark energy take control of the universe? Astronomer Brenda Fry is part of a team using massive ground-based telescopes like this one at Kitt Peak, Arizona. She peers back in time to capture the universe through its childhood, as it was growing.
Right, so this is an aluminum plate. And into this plate are drilled 640 individual holes. Each one is put at a very specific place on the mask, which will correspond to one particular galaxy on the sky.
During each observation run, the light from 640 individual galaxies is collected using fiber optic cables. The speed and relative position of each galaxy is measured to pinpoint exactly where it is in space. So far, the team has accurately mapped around 1 million galaxies in 3D, and this is what they look like. Each one of these fuzzy patches is a fully grown galaxy containing around 200 billion stars.
This is a very basic measurement, and we think that this will be able to help us to get a grasp into the nature of dark energy.
Scientists compare this adolescent universe to its baby pictures. It shows dark energy emerging when the universe is half as old as it is today.
About 8 billion years after the Big Bang, this expansion of the universe begins to accelerate, and we're in the middle of this acceleration.
The data also shows that as space expands, dark energy increases in lockstep with it.
If you had a box and you put some dark energy in it, and then you went and you weighed that box. Now you take the box, you make it twice as big. You don't open it, you don't put anything in it. You weigh it again. It's going to weigh twice as much.
This remarkable observation means we should be safe from a big rip. Dark energy will continue to increase gradually. The universe is heading for a big freeze. Scientists can finally calculate a timeline for the end of the universe. It now seems that we live in an almost perfect universe with just enough gravity to hold the galaxies together and just enough dark energy that it will expand forever without ripping itself to shreds. Cosmologists can now finally envision the end of everything.
30 years ago, it was debatable, but now it appears that the universe most likely will suffer a deep freeze.
If you look at the data, it stares out at you.
This confidence has come from our measurements of dark energy. Remarkably, these observations are unique to our time and place in the universe.
It turns out that in some cosmic sense, this is the right time to be doing cosmology.
Had human civilizations evolved much earlier, we would have seen a night sky dominated by gravity with little or no dark energy. And if we had evolved much later, we would have faced an even bigger hurdle.
Future cosmologists will not have it as easy as we do now.
Within a period of about 2 trillion years, all of the galaxies we now see will be moving away from us faster than light and will have disappeared.
With no galaxies to measure, there will be no way to detect dark energy and no way to predict the end of the universe that we're now pretty confident will unfold. A big freeze. In a big freeze, dark energy pushes galaxies further and further apart, but they remain intact. The stars inside them fade away.
Every star you see in the sky, including our sun, is burning through its nuclear fuel.
The gas will run out, stars will stop being made, and the ones that exist are it. Those are the last ones.